Tau Ceti is a relatively nearby star and one of the closest G-type stars to our solar system. Located 12 light-years away in the constellation Cetus, Tau Ceti is a single star that has a similar spectrum to our Sun's and approximately 81% of the solar mass. Tau Ceti is a stable star whose brightness barely changes and has a hydrogen-helium composition. Moreover, Tau Ceti hosts 4 confirmed exoplanets: Tau Ceti E, Tau Ceti F, Tau Ceti G, and Tau Ceti H. Curious to learn more about Tau Ceti and its planetary system? Keep watching. Tau Ceti is a main sequence star, which means that it's well into the stage of hydrogen-helium thermonuclear fusion in its core. It's a yellow-orange G-type dwarf star that's visible from Earth due to its nearby location. It's crucial to compare Tau Ceti's features to the Sun's features since it may have a habitable planet. It has a mass that's approximately 81 to 91% of the solar mass and a radius that's equal to 75 to 77% of the solar radius. However, Tau Ceti has only 59% of the solar luminosity. It's 5.8 billion years old, which means that it's older than our Sun. In addition to that, Tau Ceti is a metal-deficient star, such that it's not as enriched as the Sun in elements that are heavier than hydrogen and helium. In particular, it has approximately 22 to 89% of the iron solar abundance. Moreover, Tau Ceti has an axial period that is equal to 34 days, which means that it rotates more slowly than our Sun. Tau Ceti has a space velocity equal to 37.2 kilometers per second relative to the Sun. This space velocity is used to estimate the orbital path of Tau Ceti in the Milky Way galaxy. Moreover, it is moving with a radial velocity of 17 kilometers per second towards the Sun, which means that it will make its closest approach to the Sun in about 43,000 years, and it will be 10.6 light-years away from us during that event. Spectroscopic measurements have been used to determine most of the physical properties and features of Tau Ceti, such as radius, mass, luminosity, and its approximated age. The chemical composition of Tau Ceti reveals so much about its evolutionary status. It has a lower metal abundance than the Sun, which indicates that it's older. In order to understand this, it's worth noting that the younger stars tend to have larger portions of metals in their atmospheres than older stars, because older stars were formed at very early stages of galactic dynamics before any supernova had occurred. Supernovae are the main source of heavy metals, which are elements heavier than hydrogen. Therefore, older stars, such as Tau Ceti, are less abundant in metals than younger stars, such as our Sun. There's as much interstellar dust surrounding Tau Ceti, more than 10 times, as is present in the solar system. In particular, a large and relatively dense cold dust disk has been detected around Tau Ceti by using the sub-millimeter Common User Bolometer Array (SCUBA) of the James Clerk Maxwell Telescope at the Joint Astronomy Center on the Big Island of Hawaii. Due to the fact that Tau Ceti is a relatively old star, astronomers believe that this ring of dusty debris is most likely to be produced by collisions between larger comets and asteroids that break them down into smaller pieces. However, that dust disk is similar in size and shape to the disk of comets and asteroids that orbits our Sun, except for the fact that the Tau Ceti disk has more mass of cometary and asteroidal material than is currently observed in the solar system. This fact is completely unknown to scientists and astronomers. Simply, why would Tau Ceti have a more dense cometary disk than the Sun, although its mass is relatively less than the solar mass, such that its gravitational field is expected to attract less cometary and asteroidal material than the Sun? However, it's neither true nor completely understood until now. Moreover, the stability of Tau Ceti is probably because its atmosphere displays little or no magnetic activity at all. Studies have shown that Tau Ceti undergoes an 11-year cycle, which is weak relative to the Sun, as you probably know that every star has 3 special zones surrounding it. These zones are divided by temperature, just like Goldilocks. There's a zone that is too hot, which is the closest to the star, a zone that is too cold, which is the furthest from the star, and one zone that is just right, which is in the middle. That just right zone is called the habitable zone. Planets lying within this zone are most likely to support life. The inner edge of Tau Ceti's habitable zone is located relatively far from the star at around 0.582 AUs from the star, while the outer edge lies even further out at around 1.157 AUs. According to one type of model calculations performed for the NASA Star and Exoplanet database. Observations from the SIM project revealed that any Earth-type planet that is comfortable with liquid water would be centered around only 0.74 AU away from Tau Ceti, which is comparable to the orbital distance of Venus and Earth in the solar system. That candidate Earth-type planet would have an orbital period that's under 240 days, which is less than 2/3 of an Earth year, based on the assumption that Tau Ceti has 92% of the solar mass. The possibility of existence of Earth-type terrestrial planets around Tau Ceti is very high due to the failure to find large substellar objects like brown dwarfs or a Jupiter or Saturn-class planet in a touch orbit around Tau Ceti. In particular, astronomers using the Hubble Space Telescope have failed to find a large substellar companion around Tau Ceti so far. The search for extraterrestrial intelligence in the Tau Ceti planetary system is a very promising research area in the astrobiology field, and that is because there are many major factors that trigger this particular research interest in Tau Ceti, such as its proximity, sun-like features, along with their implications for possible habitable planets and life. Tau Ceti is categorized as a solar analog, since it has a relatively similar mass and low variability, but it's less abundant in metals compared to the Sun. Astronomy and precision radial velocity planetary searches of Tau Ceti resulted in excluding the presence of hot Jupiters and any planets that have minimal Jovian masses with orbital periods less than 15 years in the Tau Ceti planetary system. That's because these searches have ruled out any periodical variations associated with massive planets around Tau Ceti. In December of 2012, studies led by the University of Herdfortshire revealed that Tau Ceti may host at least 5 planets. 4 of them are confirmed to some extent, with one in the star's habitable zone. These studies were held by the international team of astronomers from the UK, the USA, Chile, and Australia. Moreover, they've combined more than 6,000 observations from 3 different instruments and intensively modeled the gathered data. The team of astronomers was able to develop a method to detect half the size of the previously detected signals, which greatly increased the sensitivity of searches for small planets. These noise modeling techniques were developed by adding artificial signals to the data and testing the recovered ones with a variety of different approaches. While Tau Ceti G and H exoplanets lie in the hot zone of the star, there are 2 other candidate exoplanets. Tau Ceti E and Tau Ceti F have some properties that are consistent with the habitable zone definitions. Tau Ceti E is a confirmed candidate exoplanet that is closer to Tau Ceti orbit than Tau Ceti F at a distance of approximately 0.55 AU, which is between the orbits of Venus and Mercury in the solar system. Tau Ceti E has an orbital period of 168 days and a mass of approximately 3.93 Earth masses. The surface temperature of Tau Ceti E is estimated at 68 degrees Celsius, based on the assumption that it possesses an Earth-like atmosphere. However, a 2014 study showed that Tau Ceti E partially lies outside of the habitable zone of the Tau Ceti star, and it's much closer to be a Venus-like world. On the other hand, Tau Ceti F is another candidate habitable super-Earth that orbits the Tau Ceti star at a distance of approximately 1.35 AU, which is near Mars's orbit in the solar system. It's worth noting that a super-Earth is a planet that is much larger than Earth, but not as large as a gas giant. However, don't let the name super-Earth fool you. A typical super-Earth might not have the features, physical properties, and chemical compositions that are similar to Earth's, but it gets its name because it's closer in size to Earth than a gas giant. Moreover, Tau Ceti F has an orbital period of 642 Earth days and a mass of approximately 3.93 Earth masses, despite the fact that it perfectly lies within the habitable zone of the Tau Ceti star, and according to a study that was held in 2015, there may not be a detectable biosignature on the surface of Tau Ceti F due to the fact that it has been in the temperate zone for less than 1 billion years. The potential habitability measurement of any exoplanet requires a lot of detailed data regarding the properties of that exoplanet, such as its atmosphere, spin state, surface temperature, the evolution of its volatile content, and so on. However, so far scientists were able to gather a relatively small ratio of this required data about the Tau Ceti candidate exoplanets. In particular, the only data that is available about them are very basic orbit parameters, along with a limited number of rough measurements of their sizes, masses, and some basic properties of their host star, aka Tau Ceti. Comparing the known properties of exoplanets to the current understanding of planetary habitability is the best way to determine if an exoplanet is potentially habitable, such that it is an Earth-like planet where the surface conditions allow for the existence of liquid water, which is the most important presumed prerequisite for life development. Here are the procedures by which scientists determine the potential habitability of exoplanets, in particular Tau Ceti E and Tau Ceti F. 1. First, they need to determine whether the exoplanet is a rocky planet like Earth or volatile mini-Neptunes. It's also worth noting that rocky worlds are planets that have a solid surface and are made of rocky materials. They are pretty much similar to Mercury, Venus, Earth, and Mars. Therefore, they are much smaller than gas planets like hot Jupiters. If we are going to find life like we have here on our Earth, then a rocky world would be a good place to look. Unfortunately, there is very limited data currently available to scientists about the exoplanets Tau Ceti E and Tau Ceti F. Their actual masses and radii are needed to calculate their densities and know their bulk compositions. However, the only information currently available about them are their minimum mass values and their orbital periods. 2. The second procedure to be used in order to determine if a rocky exoplanet is potentially habitable is to measure the amount of energy it receives from its host star, which is known as the effective stellar flux. More specifically, for an Earth-like planet orbiting Tau Ceti, the effective stellar flux is approximately 1.05 times that of the Earth. However, the value of the effective stellar flux is around 1.8 for the Tau Ceti E exoplanet, which obviously exceeds the limit for the habitable zone. Moreover, it's relatively comparable to Venus, which has an effective stellar flux of 1.91, such that it's definitely not habitable. On the other hand, Tau Ceti F has an effective stellar flux of 0.29, which means that it orbits Tau Ceti just outside its habitable zone. However, assuming that Tau Ceti F beats the odds and is not a mini-Neptune exoplanet, it's quite likely to be a frozen ice ball that cannot support Earth-like conditions on its surface. It also may still support some biocompatible environments below its surface where life might thrive.